This is your introduction to stoichiometry. The word stoichiometry comes from the Greek prefix stoichio, meaning element, and metry, of course, means measurement. In today's chemistry, we can use this definition. Stoichiometry is the study of the amounts of reactant used and product produced in a chemical reaction. In other words, we want to be able to calculate the amounts of reactant used and products produced in a reaction. And, as I tell all my students, you can do any stoichiometry problem if you understand this. The coefficients in the balanced equation represent the mole ratios of the species. Use these mole ratios to convert between moles of species in a reaction. For example, in this generic equation, 1 mole of A reacts with 2 moles of B to yield 1 mole of C and 2 moles of D. Notice in balanced equations, the coefficient of 1 does not have to be written. If no coefficient is written, a 1 is understood. To do stoichiometry, simply use these mole ratios to convert between species. For example, use a mole ratio of 1 to 2 to convert between A and B. Or use a mole ratio of 1 to 1 to convert between A and C. And that's it. Let's define limiting and excess reactants. In a chemical reaction, the limiting reactant is the reactant that is fully consumed. The limiting reactant runs out and the reaction stops. The limiting reactant limits the amount of product that can be formed. Therefore, we always use the limiting reactant for stoichiometry calculations. Sometimes there's more than one reactant. The excess reactant is the reactant not fully consumed. Recall, the limiting reactant runs out and some excess reactant will remain. Consider this simple example. 1 mole of A reacts with 1 mole of B. Let's identify the limiting and excess reactants. In this balanced equation, for every 1 mole of A, there are 2 moles of B that are required to react. But we're told that only 1 mole of B is present for 1 mole of A. And we need 2 moles of B. There's not enough B present to react with 1 mole of A. Therefore, B is the limiting reactant, and A is the excess reactant. Now that we've identified our limiting and excess reactants, we must always remember to use our limiting reactant, B in this case, for stoichiometry calculations. This is theoretical, actual, and percent yields. The theoretical yield is the maximum amount of product that can be produced, or 100% yield. And that's the key term here, 100% yield. Take this balanced equation, for example. For every 1 mole of A, there's a maximum of 1 mole of C that can be produced, assuming a 100% yield. This means that all the reactant, 100%, would be converted to product. What happens if not all 100% reactant is converted to product? This would be called an actual yield. The actual yield is the amount of product actually produced in an experiment, accounting for any loss of product to the environment, in other words, during any transfers or during measurement, or to side reactions. We can take the ratio of these two to get a percent yield. A percent yield is calculated to test good lab technique or manufacturing efficiency. It is defined as the actual yield divided by the theoretical yield times 100. In the combustion of methane, how many moles of CO2 are produced if 6.75 moles of CH4 reacts in excess O2, assuming 100% yield? This is a stoichiometry problem. The problem is referring to finding the amount of product. Notice the phrasing, how many moles are produced. Let's recognize a few things. First, combustion represents something reacting with oxygen. Next, notice the excess reactant O2 is named for us. We don't have to find it. This means that methane is the limiting reactant. And remember, always use the limiting reactant for stoichiometry calculations. We are given the amount of methane, and we are interested in how many moles of carbon dioxide are produced. We start with 6.75 moles of methane. We'll next set up our ratio for converting. Insert the units mole of CO2 in the numerator and mole of CH4 in the denominator. Now, the mole of CH4 will cancel. According to the balanced equation, 1 mole of methane reacts to produce 1 mole of carbon dioxide. This calculation gives us 6.75 mole of CO2 produced when 6.75 mole of CH4 reacts with excess O2, assuming a 100% yield. In the combustion of methane, how many moles of O2 are required to fully react with 5.25 moles of CH4? Notice in this problem, we're asked to find the amount of reactant, O2, not the product. We are asked how many moles are required to fully react. So this isn't a limiting reactant problem. We just need to find the amount of O2 needed to react with the 5.25 moles of methane, CH4. We are given the amount of methane, and we're interested in how many moles of oxygen react. I'll start with my 5.25 moles of methane. Then I'll set up my ratio for converting. I'll insert the units mole of O2 in the numerator and mole of CH4 in the denominator. The mole of CH4 will cancel. According to the balanced equation, 1 mole of methane reacts with 2 moles of oxygen. And this calculation gives me 10.5 moles of O2 are required to fully react with 5.25 moles of methane. Three moles of chromium reacts with excess sulfur. How many moles of sulfur fully react with 3.00 moles of chromium? First, let's recognize this is a balanced equation. 16 moles of chromium reacts with exactly 3 moles of molecular sulfur to yield 8 moles of chromium 3 sulfide. Next, notice in this problem we are asked to find the amount of reactant, molecular sulfur, S8, not the product. We are asked how many moles fully react, so this isn't a limiting reactant problem. We just need to find the amount of S8 needed to react with 3.00 moles of chromium. We are given the amount of chromium, and we're interested in how many moles of sulfur react. So we'll start with 3.00 mole of chromium. Then I'll set up my ratio for converting. I'll insert the units of mole of S8 in the numerator and mole of chromium in the denominator. Now the moles of chromium will cancel. And according to the balanced equation, 16 mole of chromium will react with 3 mole of S8. This calculation gives us 0.565 moles of S8 are required to fully react with 3.00 moles of chromium.